So let's begin by conditioning on the first step, on the first trial. Recall, W stands for the event that you win eventually at craps. W sub n stands for the event that you win on the nth trial, and Fk stands for the event that you throw a number k on the first trial. The events F2, F3 through F12 partition the space, and by an immediate appeal to total probability, to additivity, we can decompose the probability of winning by conditioning on the probability of winning having thrown k on the first trial. Very good, so far so good. Now the question is this decomposition helpful? Indeed it is. What are we given in this experiment? Let's pause and take a look. We are told that we will throw a number k with a probability pk listed on the left of your table. So we know the numbers p2, p3, p4 through p12. What else do we know? Well, we know certain conditional probabilities. We are given that if we throw 7 or 11, you win immediately. Therefore, the conditional probability of winning, having thrown a 7, is 1, and the conditional probability of winning, having thrown an 11, is also 1. And we are told that we lose immediately if you throw a 2 or a 3 or a 12. The conditional probability of winning in these cases is identically 0. You cannot possibly win, in fact you've lost, if you throw 2, 3 or 12 on the first trial. Now we can fold this into our total probability equation, and the terms corresponding to k equal to 2, 3 and 12 will vanish quietly like the snows of yesteryear. They contribute nothing to the sum because the conditional probability in those instances is identically 0. The conditional probability in the cases k equal to 7 and 11 contribute exactly 1, and therefore our sum simplifies to p7 plus p11 plus now a sum over the residual terms k running between 4, 5, 6, 8, 9 or 10. Okay, so that means we now have a conditional probability to evaluate in those residual cases. Let's move on directly and see how we can go ahead and do this. Now, here is where our second epiphany comes to mind. So, here's what we need to do. We have to determine, for the cases 4, 5, 6, 8, 9, or 10, what is the conditional probability of winning having thrown one of these numbers. Recall that in such a setting, the game progresses by throwing the dice repeatedly until you will win if the original number was thrown. Now, in such a case, it is now natural to appeal to additivity one more time and break down the chance of winning by the chance of winning on a designated trial. If you win at all, you're going to win on the first trial, or the second trial, or the third trial, and so forth. In other words, the event W is the union of the events W1, W2, W3, and so on ad infinitum. In still other words, we can write down the probability of W given Fk, where k is one of 4, 5, 6, 8, 9, or 10, as the probability of the union of the events W sub n, given that Fk has occurred, given that k was thrown on the first trial. What we've done is simply appeal to additivity and decomposed the event that you win into the pieces that you win on given trials. But the events Wn, W1, W2, W3, and so forth, are clearly mutually exclusive. They are disjoint. If you win at all, you might win on the third trial, but in that case, you haven't won on the fifth trial. These are disjoint or mutually exclusive events. And additivity immediately rides to the rescue, and so the probability of the union is a sum of the conditional probabilities. One more step is given to us by the starting conditions. Remember, we are interested in the special cases where we throw 4, 5, 6, 8, 9, or 10 on the first throw. But if you throw 4, 5, 6, 8, 9, or 10 on the first throw, then we know that the game proceeds. It does not terminate. you're going to have to make at least one more throw. In other words, for these values for k, the chance of winning on the first throw is identically 0. The probability of W1 given Fk for k 4, 5, 6, 8, 9 or 10 is 0. And therefore the first term in the sum disappears and the sum simplifies ever so slightly. It was sum for integer n ranging from the second trial onwards of the conditional probabilities of Wn given Fk. All right, we reduce the problem further. So now the conditional probabilities that we need to compute are obtained as a sum of conditional probabilities. And so the final piece of the puzzle now is for us to evaluate the conditional probability of winning on the nth trial when you have thrown k on the first trial. And we're interested in particular for the cases where k is 4, 5, 6, 8, 9 or 10, where the trials will continue after the first trial.